Okay, so let us start. So last class we have seen about the relativistic addition of velocities. Okay, and in that we have derived the relation between the velocities for two different frame of references, S frame and S prime frame. And what we have understood from that, let me just give a small recap to that. That we have seen that in case of Galilean relativity or Newtonian relativity. Am I audible to all?
Yes,
Yes,
sir,
sir.
you're audible.
Yes, sir. You are audible.
Okay. So in case of your Newtonian relativity, the velocity of a particle with respect to any reference frame, let's say S reference frame, will be equal to the sum of its velocity with respect to S prime frame and the constant velocity with which S prime frame is moving relative to S frame. This is what Newtonian relativity says. But if you follow this Newtonian relativity addition rule, then the speed of light in vacuum would be different for observers in different frame of reference. But this is against the postulate of special theory of relativity that says that speed of light is always constant. So this is a contradiction. So it is found that this Newtonian relativity rule, that means velocity addition rule, is not valid. It is wrong. So Lorentz transformation equations were applied, and as a result, when you applied Lorentz transformation equation, that gave correct addition rule. So that is known as relativistic addition of velocities. And after deriving, we have seen certain relations. Let me just write down those relations. Suppose we are moving in all the three dimensions, let's say, then ux was given as ux prime plus v divided by 1 plus v square by c square ux prime. And this is a root over. Okay, sorry, there is no root over. Yes. So this was the relation. So let's say this is equation 1a. Similarly, for uy, it was uy prime 1 minus v square by c square root over whole divided by 1 plus v by c square ux prime. I have done a small mistake. This is not v square. This has to be v by c square. Remember, when you write in this form, you should not give a root over sign here. Only when you write this gamma factor, then only you have to give here 1 minus v square by c square, that is root over. This is nothing but your 1 by 1 minus v square by c square root over. Okay. And let's say this is 1b and uz is equal to uz prime 1 minus v square by c square root over whole divided by 1 plus v by c square. This has to be ux prime. This is 1c. So these three equations are known as transformation equation of velocity. These are known as transformation equations of velocity. Okay, understood? Yes or no? So this part we have already derived. So similarly, now we will see relativistic mass, momentum, and energy. Okay. So the next topic is relativistic mass. So what do you mean by relativistic mass? What do you mean by this relativistic mass? So relativistic mass means usually we use this relativistic mass concept in nuclear physics, particle physics, astrophysics, in special theory of relativity, general theory of relativity. And the reason for this mass is that how it is different from your actual mass or rest mass. You must have read about the rest mass. So what is rest mass? Rest mass means the mass is invariant. Okay, that is the invariant quantity. That is called rest mass. So rest mass is invariant mass. Mass is not changing. If you take a example of electron, now electron when it is moving inside the atom, we can consider this relativistic mass, relativistic velocity, relativistic energy. That means this relativistic word will be used whenever a particle is moving close to speed of light. Okay, close to speed of light. Understood? Yes or no?
Yes, sir.
That means this rest mass is the invariant mass which is same for all the observers in all the reference frame. While this relativistic mass, it is dependent on velocity. It is dependent on velocity. So remember, it depends on velocity. So if this velocity increases and keeps on increasing, and when it becomes close to speed of light, then only this relativistic mass or this word relativistic will come into picture. Okay. So in a simple term, your mass is written as, let's say, m. Okay. Now this relativistic mass will be given as gamma m naught. Understood? Is it clear to all?
Yes, sir.
Yes, sir.
Okay. So if we write it in a proper way, then I will write this as m naught by 1 minus v square by c square root over. This is my relativistic mass. Okay. Understood? Let's say in a frame of reference,
Yes,
two
sir.
masses are there and they are moving. They are moving towards each other. Then let's say one mass is m1, other mass is m2. Now, if they are moving towards each other with a relativistic term, then I can say for the independent masses, let's say if you have m1 and m2, let's say for an example I'm giving, let's say they are in this frame of reference, and let's say they are now in S frame of reference, and this is the mass, and this is another mass. Let's say this is m2, this is your m1, and m1 is approaching the speed of u1, and m2 is approaching at the speed of u2. So since it is reverse in the direction, so you have to give minus sign here, and we assume that this velocity, this u1 and u2, are very much close to speed of light. You can say the word is close to speed of light, but don't say it is with speed of light, because till now experimentally it has not been proved. So anything moving close to speed of light, relativistic correction factor will come. So now my m1 will become what? It is m naught whole divided by 1 minus u1 square by c square root over. Similarly, m2 will become what? M2 will become m naught divided by 1 minus u2 square by c square, and this is root over. Okay, and in a general term, you can write like this. Okay, so m is equal to gamma m naught. This is in general expression. Okay, so now suppose I'll tell that u1 is 0. Suppose my u1 is 0. So what happens? M1 becomes m naught when u1 is equal to 0, and when m2 is equal to m naught, when u2 is equal to 0. So that is m naught is the mass of the particle at rest. So what is your m naught here? This m naught is your mass of particle. M naught is called mass of particle at rest. So this is called your rest mass. This is called your rest mass of the particle, be it electron or any other particle. And when this particle is moving close to speed of light, that means its velocity is now close to speed of light, you can say this has to be changed. So you have to write this as gamma m naught. So gamma is the correction factor which is correcting this mass. Understood? I hope it is clear to all. Okay, so this m naught is the mass of the particle at rest, and you can say it to be rest mass. It's also called rest mass. So now I hope that it is clear how this rest mass and the relativistic mass is related. If you want to write, you can write MREL. So this is relativistic mass. Is it clear to all?
Yes, sir.
Okay, so this can also be called as the proper mass. It means proper mass of the particle as it is measured in the inertial reference frame. Remember, it is measured in inertial reference frame, okay, in which particle is at rest. And m is the mass of the particle moving with certain velocity v. When that approaches nearly equal to c, then correction factor will come, and that is gamma m naught. Understood? Is it clear?
Sir, it will only happen when the V is equal to nearly equal to C.
Yes. When it is nearly equal to c. Anything moving less than the speed of light or very much less than the speed of light, no need of considering this relativistic mass. That is why we do not see any relativistic effect on Earth. We do not experience that. Okay. Okay. So in the same
Yes, sir.
way, as we found relativistic mass, we will find out the relativistic linear momentum. Numericals will be asked from this concept, what we are reading right now. Relativistic mass. What is relativistic mass? Differentiate between rest mass and relativistic mass. Differentiate between a linear momentum and a relativistic expression for linear momentum. Okay, just short answer questions and numericals. And this kind of questions, numericals, actually particularly problems, numericals, it comes in your entrance. Okay, so relativistic expression for linear momentum. Okay, so linear momentum, we know what is linear momentum. You also know that conservation of linear momentum takes place for an isolated system of a particle. These things already we have read in in our previous classes. So what is the extra factor is multiplied here, and how this relativistic expression is expressed? Let us see that. So we know that simple. We know that momentum is equal to mass into velocity. We know this, right? Now this m will be your relativistic correction factor when it comes. This is gamma m naught, and this is v. So you can write this as m naught multiplied with v divided by 1 minus v square by c square root over. Okay, understood?
Yes, sir. Yes, sir.
Okay. Similarly, we will find expression for force. Expression for force. So according to Newton's second law, what we know? We know that it is the time rate of change of momentum. So it is dp by dt. So now I can write it as d by dt, and p we know this is m naught v divided by 1 minus v square by c square root over. Okay. So if you to take the derivative of this, okay, take the partial derivative, and after doing this mathematical calculations, I'm just writing the direct formula. So you solve this one. This is your homework. Okay. You solve this part and try to deduce this form. This can come as a short question. So f is equal to m naught by, this is 1 minus v square by c square uh, in bracket. This becomes 3 by 2 and a. So isn't it ma? Isn't it like ma? So in place of m, you are getting this factor because of your derivative. It is not exactly 1 minus v square by c square root over. It is becoming 3 by 2. So that will give you gamma cube m naught. Why? Because what is your gamma? It is 1 by 2, isn't it? This is root over. So now it is 3. So 3 into 1 by 2, so it is gamma cube. m naught a. Okay, and what is your a? It is the time rate of change of velocity, acceleration of the particle. So this equation shows that the net force acting on a particle is not only directly proportional to acceleration, it is also dependent on this gamma factor. Because if you remove this factor, the force is just like a non-relativistic force ma. But under relativistic correction, this becomes gamma cube m naught a. Is that clear to all? Yes or no?
Yes, sir.
Okay. So I'll take a small example. Try to solve this one. Question is, a 1 kg car, a 1 kg car is moving at 10 meter per second. Find its increase in mass. Okay. All of it take 5 minutes. After that, I'll discuss this one. Try to do it. Try to understand the question. What is given? M is given to you. Which M is this? This is the rest mass. Initially, the car mass was 1 kg, or you can take in terms of gram if you want to take. You can take 1000 gram. Sorry. The question is not 1 kg. This is actually 1000 kg. Wait. A car cannot be 1 kg, no? Yes. So this is 1000 kg. Okay. So mass is given. So that is the rest mass is given to you. Velocity is given, that is 10 meter per second. And C you already know. Okay. So
सर
now you have to.
वेलोसिटी तो लाइट के उससे बहुत कम है सी से.
Oh, so what happened? Increase in mass. See, we actually do not experience this kind of things. जितना आप close to speed of light जाओगे उतना आपको वो ये चीजें पता चलेगा. But if the question is asked to find out, then you have to use the relativistic correction factors here. Okay, try to find out. Simple question is just some numerical and some values are given. Substitute and find out. Okay, so I'll give you hint that m naught is given to you, that is 1000 kg, and v is given to you, that is 10 meter per second. So find out what is v by c. So 10 and this is 3 into 10, so this becomes roughly how much? Something into 10 to the power minus 9, isn't it? So please solve it.
So V by C equal to T to 10 to the power minus 7. So
How
V
much?
by T to 10 to the power minus 7.
ओके सॉल्व करो, सॉल्व देखो आंसर कितना आ रहा है. Okay, so are you all able to do it? Avinav, Dipali, Deepak,
सर
yes.
सर 1 माइनस 9 10 माइनस 14 को 1 ही ले सकते हैं ना सर, इतना मतलब माइनस में जो है उसको रिस्पेक्ट तो बहुत कम हो जा रहा है.
Yes, you can take that. You can assume that. Deepak, are you doing?
Yes. Yes, sir.
Nitish?
Yes, sir. Doing, sir.
Okay. Adya,
Yes, sir.
Avinav,
Yes, sir.
okay, so solve this one. This is your assignment. You solve it. So now we'll come to the next expression, next most important expression of Einstein, that is relativistic kinetic energy. This is relativistic kinetic energy. Okay. So what is relativistic kinetic energy? It is the kinetic energy of a relativistic particle. अगर एक particle relativistic motion में move कर रहा है, if it is a relativistic particle, then that kinetic energy is called a relativistic kinetic energy. And that is how it is defined. It is defined as the work done in increasing the speed of a particle from initial to the final value. So initially, definitely the speed of particle will be 0 because it is at rest. Now it is starting. So from 0 to the final value, so that work done in increasing the speed of the particle is called the relativistic kinetic energy of the particle. So according to the definition, I can write this K as F dot dr or ds, you know, F dot ds, work done. So F dot dr, and this is from initial to final value. Okay, and what is your F here? This F is your net force acting on the particle. Okay, so this F is your net force acting on particle. Okay, and I and F, these are the initial and final state. Okay, that means initially the speed is 0 and finally you have to find some final value, some finite value is there. Okay, so for simplicity, let us solve this one. This let us assume that the force and the displacement are along the x-axis. Let us assume. Let's assume that force and displacement are along x-axis. So F dot dr, F dot dr जो था, dr मीनिंग के dx dy dz, अभी क्या हो जाएगा आपका F dx, isn't it? This is for simplicity I have written. Yes or no?
Yes, sir.
Okay. So as a result, if I solve this, and also yes, I know that F is dp by dt, and what is my dx? How can I find dx? So I know that the velocity is dx by dt just by time. So in that way, I can write since F is equal to dp by dt and your v is equal to dx by dt. So F dx is equal to dp by dt, and ds is what? V dt, right? This is V dt. If I solve this one, what I'll get? I'll get V dp, isn't it? This is velocity. Okay, V dp, isn't it? Yes or no? And what is my dp? This is d of mv. Yes or no? Are you following or not?
Yes, sir.
Yes,
Yes,
सिंपल
sir.
मैथमेटिक्स. ओके, बीच बीच में यस सर बोलते रहो, पता नहीं नेटवर्क रहता है कि नहीं रहता है. ओके, so I should know that it is audible and clearly visible.
आज
Okay,
नेटवर्क
so
मस्त है सर. आज
so
नेटवर्क
now I
मस्त
can
है.
write this as, and now I can write this as V. Yes, something you're telling, Abhinav?
नो
Any
सर, मैंने
problem?
नहीं बोला. नो सर.
कोई कुछ बोल रहा था. Okay, any doubt? Somebody was telling something.
सर मैं बोल रहा था कि आज नेटवर्क बहुत सही चल रहा है, कोई प्रॉब्लम नहीं
अच्छा.
हो रहा है.
Oh, that's a good thing. Okay, so let's keep this as V, and let's take the advantage of this good network and complete this as soon as possible. So now this d of mv, so do the partial one. Okay, so what you will get? dmv plus m dv. जो स्टेप समझ में ना आए पूछना, ठीक है? सो mb dv plus v square dm. I can write like this. Okay, therefore now k is equal to your mv dv plus v square dm, and the limit will be from I to f. Okay, so this initial speed and this is the final speed. Initial speed has to be 0 because it is starting, and f will have some finite value v that I don't know. Let it be v. This is your equation. Okay, equation number we should give. So this is equation 1, this is equation 2, this is equation 3, and this is 4. Okay, here we can see that it is written m, and since I am doing relativistic correction here, so according to that your m will be here, your m can be written as like this, that is m naught 1 minus b square by c square root over. Is it clear, Deepak? Is it
Yes,
fine
sir.
up to here?
Yes, sir.
Okay, so now just substitute karo. Okay, so what I will get? I'll get m square 1 minus v square by c square is equal to m naught square. Isn't it? I'm taking the squaring of this one. You can give this equation 5. इसका squaring अगर हम करेंगे तो m square, this comes this side, this is m naught square. Okay, and this implies m square c square minus m square v square, and by c square will come here, it goes to this side, this becomes m naught square c square. So taking differential of both sides, we have that to the differentials of this. So what you will do? Yes. So this will be what? 2m और ये होगा c square and ये dm होगा, and this will be m square 2v dv plus 2 v square, and this is 2m actually. Okay, I'll write here m dm. This will be in bracket. Okay, and this is equal to 0. Are you following? So this implies 2m c square dm, if I put a bracket here, minus mv dv minus v square dm equals to 0. I'm taking 2m common from all. Okay, this implies c square dm minus mv dv minus v square dm equals to 0. This implies mv dv plus v square dm, taking this to this side and taking minus common from all, you will get this minus becomes plus. So this is c square dm. Okay, I have taken this first term to the right hand side and I have taken minus common from all. So this is the equation.
Sir, can you please go scroll a little?
Yes. Likho, everybody write properly. And try to relate this factor, this with your kinetic energy expression of equation 5. Inside the integration, we have mv dv plus v square dm. So in that place, I will write c square dm. Okay. So as a result, shall I continue?
Yes, sir.
Okay. Substituting equation 6 in 5. You see this part? This first term, first and second term, or you can say LHS. LHS is same as, what is that equation? Oh, it's equation 4, not 5. Equation 4. Okay. So if you substitute, what you will get? You will get k is equal to c square is constant, so bring it out. So integration of dm. So integration of dm. So dm integration कहाँ से कहाँ तक होगा? When the object or when the particle was not under relativistic correction, when it is
M not to
like a
M.
rest mass. Yes, very good. So
M
when
not
it is
to M.
at a rest mass, तो ये होगा m naught. Very good. And m, जो m होगा उसका आंसर. Okay. So m naught to m. This is important. Understanding the limit. It will be helpful for doing numericals in your exam. Okay. So now what we will do is k is equal to m minus m naught c square. Isn't it? Upper limit minus lower limit. Okay. So I can write if I take m naught common from here, then what I can write? अगर m c square, actually ये क्या है? ये है आपका m c square minus m naught c square. Now I will take m naught common from both. So if I take m naught common, I have to bring a gamma here. Isn't it? Okay. Because we know m is what? M is nothing but your gamma m naught. Okay. So equation number 7. So this is the relation of kinetic energy of a particle, relativistic kinetic energy of a particle. So now if you substitute this gamma value, I can write this k as m naught c square, and this will be 1 minus v square by c square to the power of minus half, and this is minus 1. This is equation 8. Okay. Isn't it correct? Now here we will get certain conditions. Have we completed writing up to this? Have we completed? Please respond. Am I audible?
Yes, sir, completed.
Yes, sir, completed.
Okay. Okay. So we will use the conditions. Now the first condition is if speed, for speed, let's say v is less than c greater than 0 and this is equal to 1, then what happens? Then k is greater than m naught c square. Okay, k is greater than m naught c square. For a particle at rest, if I take any particle that is at rest, or particle at rest, that means what? That means your m is equal to m naught and k is equal to 0. Is it clear?
Yes, sir.
Yes, sir.
Okay. And we will see how our classical mechanics is coming when we consider for speed extremely small. When you take this small, then this gamma, that is your 1 minus v square by c square power minus half, this can be expanded binomially. Okay. For speed extremely small, this is expanded binomially, and when you use this value in your kinetic energy expression here in equation 8, you will see that your k has have become m naught c square, sorry, m naught square c square half v square by c square. So if you do the solving, if you solve it, c square gets cancelled. This is equal to half m naught v square. Okay. So this is your, if you, and in this condition, what you have to do is you have to neglect here. Remember here your v square by c square is much less than 1. So when you do this binomial expansion, then you have to neglect other terms except this linear term. Okay, other terms will be neglected. So you got v square by c square here. So m naught square c square half v square c square gets cancelled. Sorry, this is not m naught square, this is m naught. Okay, yes. So you got half m naught v square. Doesn't it look like half mv square, which you are already acquainted with? So the non-relativistic
Yes, sir.
expression for kinetic energy having rest mass m naught moving with certain speed v is given as k is equal to half mv square, which you already know. This is the classical expression. Okay, so this expression is your classical expression. Okay, is it clear? Okay, so from this expression we will proceed to the total energy. We now proceed to,
Sir,
yes,
sir, like we have that momentum wala term also. So can we find by using the relation between kinetic energy and linear momentum? Kinetic energy equals to p square by 2m.
energy is equal to p square by 2m. You can use it.
Okay, sir.
Okay. Okay. One thing we need to remember here when we are talking about total energy, because we know that usually total energy is equal to kinetic energy plus potential energy. We have seen about the potential energy, sorry, kinetic energy factor. We have seen here just before this. Okay, this one, equation 8. What about potential energy? Here, potential energy is not included. Why? Because the particle is moving, so the potential energy is neglected. Okay, so here you have to remember that it does not include potential energy of the particle. Okay, it does not include potential energy of the particle. Is that clear? So, are you able to understand or not? Shall I proceed?
Yes, sir.
So, from this expression, are you all taking the notes? Dipali, Deepak, Nitish,
Yes, sir.
Deepak,
Yes, sir.
Deepak, are you there? Abhinav?
Yes, sir.
Okay. So, in case of total energy, it does not include potential energy of the particle. Okay. So, from my expression, that is equation number 8, from equation 8, that is total energy, sorry, kinetic energy, we can write from equation 8, I can write K plus m naught c square is equal to mc square. Okay, that means this is my E, total energy. Okay, so ultimately what I got, this implies E is equal to mc square. Okay, this is equation number 9. So for any particle, let's say, कहाँ चला गया? Where is the page? Just a second, wait. Yes. So I got E equal to mc square. From here, if I consider, suppose for a particle is moving with speed 0, then I can say that K is 0. Okay, K part is 0. For the particle with speed 0, your K plus m naught c square जो था, K part becomes 0. Okay, that means your E has become E naught. That E naught is called rest energy of the particle. Even though the particle suppose that particle is it can exhibit relativistic motion, relativistic energy, relativistic mass, velocity, momentum, everything. But if the particle is at rest, that means it has the rest energy of the particle, and that rest energy of the particle is called m naught c square. Okay, so when that particle will start moving with a relativistic motion, then it will experience that gamma factor. Okay, and you will get relativistic correction factors there. There is relativistic mass, momentum, velocity, force, everything. Okay, so in that case, for a particle with speed 0, for a particle with speed 0, your k becomes 0. Okay, so E becomes E naught, and this E naught is called rest energy of the particle having rest mass m naught. Understood? So as a result, this E equal to mc square will become E naught is equal to m naught c square. Okay. That means what? This can be considered as the potential term or potential factor, because E is what? E is the sum of the kinetic energy as well as, actually ideally what happens? Total energy is sum of kinetic and potential. In your case, you have seen total energy is equal to sum of kinetic energy and rest energy of the particle. अगर kinetic energy 0 हो जाता है तो ये हुआ आपका rest energy. This is what? If you look at this equation, this K is the kinetic energy of particle, and this m naught c square is the rest energy of the particle. This is the rest energy of particle. So that means this relativistic energy is the sum of kinetic energy of particle and the rest energy of the particle. So if the kinetic energy of the particle becomes 0 for the particle having speed 0, that means the particle is at rest. So if the particle is at rest, it will have rest mass. It will not have relativistic mass. Okay, so in that case, I can say my E becomes E naught, and E naught is equal to mc square, m naught c square, where m naught is the rest mass. Understood? And here we have to consider that the total energy do not include potential energy. Okay, so this is called your energy and mass equivalence relation. So the difference between total energy and rest energy of the particle is called the kinetic energy of the particle. So what we conclude from this above two expressions, if you give equation number this 9 and this is 10, so we conclude that here the difference between the total energy and rest energy, okay, of the particle is called its kinetic energy. आया समझ में? Understood or not? So this thing can be correlated with your astrophysics, that when people believe that Big Bang has occurred, and at that time if any particle has ejected after the Big Bang, those particles are continuously, they are moving, they can never come into rest. They are completely moving, continuously moving, and they are moving close to speed of light. Okay, so the difference between the total energy and rest energy of the particle is called its kinetic energy. That helps it in moving with the speed of light, close to speed of light, you can say, or if it's a photon, then it is the speed of light itself. Okay, any doubt you have up to here? Anybody
sir.
having any doubt? Okay, very
No, sir.
good. So we can rewrite this equation 9, that is total equation, okay, total energy relation. So rewriting equation 9, we have the expression that is E equal to m naught, mc square, and that m is what? Gamma m naught. You know that? That means this is the relativistic energy. Which energy is this? This is the relativistic energy. So this is gamma m naught c square. That can be written as m naught c square by 1 minus v square by c square root over. Okay. This can further be written as, this implies E is equal to gamma E naught. I can write in this form also. Why? Because m naught c square by 1 minus v square c square from equation 10. What is your m naught c square? This m naught c square is called your E naught by 1 minus v square by c square. So E is equal to gamma E naught. So whenever you don't have this relativistic factor, then for the classical limit you have, this is called E naught, m naught c square. Okay. So this is the relation. So I can say, let us, this is equation 11. So I can say that E naught is the rest energy of the particle. Now, in terms of its momentum, if you want to find out, in terms of its momentum, see, because here a very interesting concept you will come across, what Einstein has given, that regarding photon, what he said that जब से Big Bang start हुआ, when the Big Bang occurred, if the first initial photons when generated, since then till now they are moving continuously with speed of light, because photon is nothing but light. It is moving with c speed. Okay, and if any object or if any particle is able to move with light speed, not close to light speed, I'm talking about the photon itself. If the photon is moving with light speed, then it is not having mass. And since photon is not having mass, how it is possible that it is having energy? First question. Then how it is possible that light travels in a straight line or in a curved path? Later on, Einstein said that light travels in a curved path, because curved path is the most easiest and the shortest route. How it is possible? Third point, when total eclipse took place, when Einstein gave this concept and when Eddington proved that yes, gravity bends light, then how can gravity bend light if light is not having any mass? How can it interact? So many questions arise at that time. Okay, so very beautifully this expression has been given by Einstein. Let us see in a very simple form, that we understood that this relativistic energy is now related with gamma E naught, and that is your equation number 11. So this is your relativistic energy, and this is your rest mass energy. Remember, E naught is your rest energy. Okay, so while expressing expression of total energy in terms of momentum. Okay, so what happened? What he said that let us square equation number, this total energy expression, I think 9 or 10, 9. Let us square this equation 9. So when you square equation 9, squaring equation 9, you got E square is equal to m square C4, and m square, that means this is your m naught square C4 whole divided by 1 minus b square by c square root over, since it is square, root over is gone. Okay, so it is m naught square c4 by 1 minus b square by c square. This implies E square minus m naught square C4. Okay, this is equal to m naught square C4 1 by 1 minus v square by c square minus 1. Is it correct? Simple mathematics. What I have done, both the sides I have subtracted this factor. Look at here. From this above expression, from LHS, I have subtracted m naught square C4. Similarly, from RHS, I have subtracted m naught square C4. Okay? Simple? Yes or no?
Yes, sir.
Now solve it. So this will be your m naught square C4. This is 1 minus v square by c square. If you take the LCM and if you solve it, this will become p square by c square whole divided by 1 minus v square by c square. Is that okay?
Yes, sir.
Okay. This is equal to, हर एक स्टेप देखो समझ में आ रहा है कि नहीं आ रहा है ना. सिंपली do the calculation. So this is v square by c square divided by 1 minus v square by c square multiplied with m naught square c4. So this can be written as c square v square m naught square whole divided by 1 minus v square by c square. Is it correct? Did you find this answer? Okay. Deepali, are you doing? Deepak, am I audible to all?
Yes, sir.
Okay.
Audible, sir.
Okay. Pinaki, Adya,
Yes, sir.
Abhinav.
Yes, sir.
Okay. So can I write this in this form? Yes, can I write?
Yes, sir.
Okay. Now, can I write in this form? Can I write?
Sir, screen
Yes, sir.
froze.
बोलो
c
क्या
square
हुआ?
plus c square p square पे हो सकता है ना सर मोमेंटम.
But sir, it's E square is equals to P square C square plus MC square का whole square.
नहीं समझ में नहीं आया, क्या पूछ रहे हो?
सर आगे टर्म नहीं आएगी क्या प्लस MC स्क्वायर का whole square?
आएगा ना, यहाँ से मैं आगे लाऊंगा. यहाँ पे तो ये है टर्म, ये आगे आएगा, फिर ये इधर. Now I am just solving this part. Okay. So after
Yes,
that,
yes, sir.
हाँ, तो जो तुम बोल रहे हो वो बोल रहे हो कि ई स्क्वायर के फॉर्म में. अभी मैंने उसको लिखा नहीं है. Okay. So now what I will do is, as Deepak was telling, so this is your E square is equal to C square P square. That factor will come to this side. So this is your M naught square C4. So final expression is E is equal to M naught square C4 plus C square P square root over. Okay. So this is my relation of total energy with momentum. Okay. This is what? Relation between total energy and momentum. Is that clear? So E is equal to m naught square c4 plus c square p square. You can give some equation number. What is the continuing equation number here? After 11, you got
This was 12.
equation. Yes, what? Anybody is telling anything?
12.
Okay, yes, yes. Equation 12, right. So now we will see for massless particle. Yes. So E is equal to root over of m naught square c4 plus c square p square. Now let us find the expression for a massless particle. Energy and momentum for massless particle. Okay, so the example of this massless particle is photon. Photon is massless. This implies the rest mass of photon is 0. So as a result, from equation 12, what we can say that E is equal to, now m naught becomes 0, so this factor is gone. So it is what? C square p square root over, that is nothing but your Cp. Okay, so this implies your momentum is equal to energy by C. Okay, so the reason for photon experiencing gravity, photon bending due to gravity, or bending of light due to gravity, or the photon moving so fast continuously, it is not coming into rest. All these things are associated with the momentum. Even though photon is not having a mass, it is having momentum. But if you think classically, is it possible any particle not having mass having momentum?
सर वही पूछने वाला था सर.
No, sir.
सर फोटोन
Yes.
मतलब मोमेंटम इज इक्वल टू मास इनटू वेलोसिटी. तो मास ही
Yes.
अगर नहीं तो ये कैसे आ रहा है सर? मोमेंटम कैसे आ जा रहा है उसका?
वही तो हमने अभी ड्राइव किया ना, तो वहीं से आ रहा है. दिस इज व्हाट द डेरिवेशन, दिस इज द ब्यूटी व्हाट आइंस्टाइन हैज गिवन. लॉरेंस ने तो बहुत कुछ बताया था. सो लॉरेंस gave many concepts, many things. So we got relativistic correction factor from momentum, mass, energy, everything. But the way Einstein has related energy and mass, and most important factor is the light, photon. Okay, so about light he has given this beautiful concept. So how nicely he has tried to relate all these things, you see. So because when relativity was studied, when Einstein relativity was studied, because earlier it was all about Newtonian relativity. And in Newtonian relativity, we know that nothing is moving close to speed of light. Everything is moving with a very less speed. So your Galilean transformation was correct. When Lorentz transformation was found for higher velocities, then this question came into picture, that how light, if light is a photon is massless, then how it is moving, how it is not coming into rest, why its speed is not decreasing or not increasing, it is a constant speed. And if it is a massless, how it is moving, how it is bending, and bending of light experiment, what Eddington has done, what Einstein has predicted about the star relative displacement of star behind the sun during eclipse, it was exactly accurately, it was to that value he has given, exact value, you cannot say close. So how precisely Einstein could do this thing? Because he knew that the photon being massless, it is having momentum, and momentum is the main reason for all these things. And he has never considered gravity as a force. He has considered gravity as a curvature of space-time, or wrapping between space and time. That is space-time. Okay. Understood? So from this concept, equation number 13, he will give mass energy equivalence, which you know already. That is mass energy equivalence. See, this mass energy equivalence concept is also well accepted in your particle as well as nuclear physics, because you know that whenever a nucleus disintegrates, nuclear fission takes place. When a bigger nuclei bombarded with a fast moving neutrons, it undergoes nuclear fission reaction. Two daughter nuclei is formed. Then if you add the constituent masses of those daughter nuclei, you will not get it to be same as the parent nucleus. But it's a very small difference. At that time, this small difference could not be explained by nuclear physicists at that time, until this mass energy equivalence relation was accepted. So there also this relativistic factor comes into picture. That is photons, this quarks, or usually this quarks is the building blocks of protons and neutrons. So just a second. Class रे अच्छी परे परे कॉल କରୁଛି क्लास रे अच्छी କରୁଛି 10 मिनट ପରେ. Okay, so what I was telling, yes, so this mass energy relation is the important, very important while explaining this small mass defect or binding energy per nucleons in nuclear physics also. Okay, so according to Einstein, what is this mass energy equivalence? He said that the mass of a body is a measure of its energy content. So what is the statement? He stated that even if you want to understand this mass energy equivalence, you can see in a YouTube a live video of Einstein is there. Okay, there he is explaining this thing. You can search it. It's a 2 to 3 minute video, or else after the class I'll show it to you. So what he's telling that mass of a body is a measure of its energy content in the system. Okay, energy content. That means the energy of the body always equals to mc square. And he said that mass and energy are equivalent. That means anything having mass has energy. Anything. So any small to small object, think of anything having mass. Maybe that is massless for you, but if it is having some finite value, okay, 10 to the power kuch bhi ho jaye, smallest, even much small than electron also, that is also having energy. And this concept of Einstein was actually used by Peter Higgs to give this Higgs boson concept. Okay, Higgs field.
Sir?
Yes.
Sir, as per the statement, anything having any mass, but photon doesn't have any mass, then how it having the energy?
He has explained according to relativistic factor, relativistic energy. He has taken, no, just now we have done that. That is why I have solved it for you. That is the reason today I have taken it long class. Okay, because this things requires a continuous teaching. If I break in between, it will be difficult. So यहाँ पे देखो कैसे उन्होंने explain किया. How? Initially he has taken mass. You see how he has taken mass तो था ना initially, but now what he has done? He has written energy. See, he has written energy, or he has given a formula of relation between energy, total energy and momentum. Okay, लोग momentum के बारे में नहीं सोच रहे थे. Momentum को उन्होंने यहाँ पे लिया. He is not telling that. If you see, very simple thing, mass यहाँ नहीं है, लेकिन momentum है. Momentum है मतलब कुछ तो mass होना चाहिए उसमें. लेकिन उसका स्पीड इतना है, इतना मतलब क्या, लाइट का स्पीड तो लाइट का स्पीड ही है, वो किसी के बराबर तो नहीं है. इट इज द एक्सट्रीम स्पीड वी हैव टिल डेट. तो उस केस में ही massless particle can behave or can interact with other things due to this momentum. जब उसका स्पीड लाइट के स्पीड से, अगर कोई और ऑब्जेक्ट होता उसका स्पीड लाइट के स्पीड से थोड़ा सा भी कम होता, then along with momentum some finite mass would have come. So that is what he has said. He has told that it is the manifestation of mass and energy. Okay, so mass of a body is a measure of its energy content. So if a body gains or lose any kind of energy, its mass changes, and the change in mass is given by this change in mass is ultimately given by delta m is equal to delta E by T square. Okay, but in our daily life, these small energy changes are so small that we are unable to trace it. Okay, but during high energy processes like nuclear fission, nuclear fusion, large amount of energy is released. If you see, if you have studied nuclear fusion, you can see that a 1 gram of hydrogen completely converting into helium releases some mega electron volts of energy. While you see this binding energy of electron, it is in the range of electron volt, but binding energy of nucleons, it is in the range of mega electron volt. So this mass energy conversion, this proton neutron conversion, or this protium, they will fuse, they will give rise to deuterium, protium gives rise to tritium with a protium gives rise to helium 2 3, then helium 2 3 interacts with another protium, then it gives a that inert helium, and that helium is now stable. तो ये प्रोसेस हाइड्रोजन से मतलब प्रोटियम से हीलियम तक आने में ही इतना अमाउंट ऑफ एनर्जी निकल जाता है. जस्ट थिंक sun is having, sun at its core, it is having millions to the power millions of hydrogen atoms. So how much energy must be coming out of it? Okay, so let's not discuss that part. So what we understood here is that equivalence between mass and energy is a important consequence of special theory of relativity. Okay, equivalence of mass and energy is one of the most important consequences of special theory of relativity. Okay, and mass energy equivalence also satisfies the conservation principle. That is, total mass of the system will be automatically conserved, and if it is conserved, then it implies that energy will also be conserved. Okay, so this is the relation of mass energy equivalence. So I hope that it is clear to all. Yes or no?
Yes, sir.
Yes, sir.
Okay, so this completes your syllabus. So special theory of relativity यहाँ तक हम पढ़ेंगे, उसके आगे नहीं. This is just a very brief thing what we have read, just preliminary concepts what we have read so far. So this completes your syllabus of first semester. Okay, so I hope that whatever is taught to you, it is clear to you. If you have any doubts, then we have time also, we can discuss.